Then we come to our next presentation. So welcome on stage, Dr. von Vacano. So he's the Vice President of Plant Circularity Research at BASF, so one of the big players in the chemical branch. We definitely have to work hand in hand together. Hand in hand together. So we are excited to have you here on stage and to get an overview of what we also discussed during the last two topics. The topic of how can this go hand in hand, which technologies we have, and when this presentator is not working, I think you have to keep this a little bit up. So, welcome on stage.
Thank you very much, and thank you all for your interest. What I want to do today in the next 15 minutes is to take you on a journey how to create circularity for plastics and looking at matching all these recycling technologies that we've seen on the slide before. You have mechanical recycling, chemical recycling in many flavors, how to match it to the task at hand. And the task at hand is in principle defined by what you get, the waste, and what you need to get to the product you want to make again. I talked about a journey. It is really a journey that goes along the whole life cycle of plastics. And if we want to create circularity, we need to look at how to make polymers. We need to look at how they are used. We talked about consumer behavior that could be part of a change also in the use patterns. But then in the end, we will need always some way of creating a circular end of life. We don't want to go towards the linear value chains of today, which end in incineration or landfilling, or even worse, sort of littering. And this is what I want to do today. A journey always needs, if you want to take a nice vacation, you need to focus on something. I focus on recycling, and I want to give us the navigation system to navigate on this journey in the recycling space. Recycling can be done, as mentioned, using mechanical processing only. It can be done using chemistry. And let's start with a look at mechanical recycling. As you know, this can always be done if the polymer is sort of available in a waste stream that is reasonably pure or can be sorted to be pure. If you do the sorting, then in the end you would also get a fraction that is not recyclable or that you sorted out, right? So this is always, in sorting you create a pure fraction, but that also means you create an unpure residue. If you get a material that is nicely pure and that also has a polymer structure that allows you to reshape the polymer and melt it, you can do mechanical recycling. So the polymer stays as it is, and you have the most energy efficient loop you can think of. You can do this, for example, with thermoplastic polyurethane. This is a specific polyurethane grade that behaves like a thermoplast. It can be molten. It's typically extruded. You'll find it in many applications, for example, in footwear. And whenever you get to a clean waste stream that could be post-industrial or could be collected post-consumer after sorting and a suitable waste stream. If it's clean enough, you can take the material, it's thermoplastic, you can incorporate it again, and then you end up with a grade of recycled content TPU that is available commercially today. But you can also think of mechanical recycling of materials that today cannot be mechanically recycled. For example, reactively foamed polyurethane in a flex foam typically is cross-linked, and you would always say you cannot melt it, you cannot re-extrude it, it will just crumble into pieces, which are not useful for any high-value application. But you can tweak the molecular structure of such PU that it can be still processed in the same way, it can perform the same tasks as a foam, for example here in a seat cushion that many of you might want if you're sitting on the hard benches. A seat cushion, right? A foam PU that is resilient and comfortable and has a lot of elasticity. But if you tweak the molecular structure, you can make the foam in such a way that it can be melted. It can be liquefied at high temperature. And if you do that, you can mechanically recycle it. Because now you can redisperse it, redissolve it in its own polyol and go back into the same seat foam again. So you can take 100% of the old foam and put it into a new cushion. This is something that is quite new, and we are happy to have launched this together with Vitra. And if you're interested, you can learn more about it at the booth. But even that might, at some point, you might run into problems if your waste stream is not as clean. if it's not possible to sort it to that high degree. That is, for example, a typical task you have if you have black plastics from automotive shredder residue. It's very hard to sort. You can sort it, but not to the quality that you need for mechanical recycling. But what you can do is you can still stay with the physical recycling technology, just dissolving selectively one type of polymer, keeping the polymer chains intact, and then separating and purifying at the same time in dissolution-based or solvent-based recycling. And this is something we demonstrated using real-life automotive shredder residue, so shredding cars, taking the light shredder fraction, and then doing the best sorting we can do today for black plastics, which enriches the polyamide fraction to a very high purity. But what you cannot do is you cannot separate out polyamide 6 from polyamide 6,6. So it's not a feedstock, and there's also a lot of other dirt and residual contaminants in it. So it's not a feedstock that could be used for any high-value mechanical recycling, especially for polyamides, which need to go into car parts of high structural integrity and the highest quality standards. But what you can do is you can use a suitable solvent, selectively dissolve PA6 or PA66. In this case, we took the PA6, cleaned it up, and reprocessed it together with a customer, Pöppelmann, into a real qualified car part that you can also see showcased. A car part engineering plastics from automotive shredder residue back into a high-value application that is sort of suitable for automotive standards. But still, with this kind of dissolution recycling, you're still relying on the polymer chain being intact. So the chain needs to be as long as you need it for good mechanical properties. If you have any use scenario at high temperatures or chemical stress, oxidation, and so on, where you damage chains, it will be difficult because the physical recycling cannot reconnect bonds. It cannot reconnect the chain. What you can do then is you take a material which also needs to be reasonably pure, because otherwise you will never get a commercially viable process. So you need a material which can be cleaved chemically, can be sort of cleaved into the monomers in this case. So only one step back in polymerization, and then you could take those monomers, clean them up, distill them, do chemical sort of processing, and go back into the material. One example where we have done that is using rigid polyurethane foam from fridges, highly cross-linked material. You use a chemical process to break it down, make a new material out of it that then can be used in the same application. So we reproduced a fridge with Liebherr that contains a high percentage of old recycled PU in the PU insulation. So going back to the application of the same quality, same standard, and using depolymerization to achieve this. The same is the case with a feedstock that is not very clean, that is textiles. You can sort textiles, for example, for polyamide textiles, but even within a polyamide textile, you will have lots of foreign materials because textiles are composites. Even you have elastic fibers in it, you have maybe a percentage of other fibers to tweak the properties, or even you have stitching yarn, which is a different material. So it's not a fraction that is used for mechanical recycling today and could never go into fibers, which need to have very high quality, no fluctuations in viscosity, no particles. But what you can do is you can depolymerize it. And this is depolymerization of post-consumer textile waste into polyamide that can go back into textile applications is something that BASF has launched as a Lupamid brand. And finally, also in automotive plastics, if you get a dismantled part like oil pans that have had quite some stress, chemical stress, thermal stress, you can take this fraction, depolymerize it using a similar technology like for the textiles, go back to the monomer, clean it up, and go back to car parts. And this is obviously a structural car part, a stabilizer link, right? That it needs to really, it cannot fail. So it needs to have the same quality. This is another example where post-consumer automotive engineering plastics were taken back into 100% recycled content automotive engineering plastics application. And then finally, if you do the sorting, if you look at all the different approaches we've seen, you always create a fraction where you have taken out your valuable polyamide. There's still something left, because sorting means taking something out and leaving something over. It might also be the case that you have fractions where it's just not economical to sort out % of some material which is intrinsically sort of mixed in. In this case, we need to find a way to avoid that this mixed fractions, complex contaminated fractions, are incinerated, because that generates CO2 and that sort of leaves the carbon that is a potential raw material out of the circle, and the only thing you could do is go back via CO2, which it needs very much energy. So what you can do is you can take these mixed fractions and use a technology where they are gasified to syngas. And I want to show you how that can look like. This gasification technology is also used today to create synthetic aviation fuel from biomass. But we have shown that you can use the same technology and sort of have a mixed feeding of automotive shredder residue together with biomass in gasification. And then you create hydrocarbon feedstocks which have perfect quality and can be used sort of as petrochemical replacement in the production. So what you do, you create the syngas, you convert it into hydrocarbon fractions, and these fractions are used instead of naphtha in a fossil production chain. And then using mass balance, you allocate sort of the carbon, because you're using the same assets. It's of course mixed in. We don't have the the volumes to operate a single steam cracker with that. So we need some sort of allocation mechanism. But then you can go back and make every material that you can make out of fossil based on a feedstock replacement, which something that came out of really the most horrible waste you can think of. And we've done that together with partner BEST in Austria for the gasification technology, and ZF and Porsche finally, to demonstrate that you can do it and create a steering wheel based all on material that has sort of replaced feedstock that came from automotive shredder residue. So the navigation system that tells you how to get from a specific waste to a product of quality which you need will need to take into account all these factors. And of course, it will also need to look at cost and CO2, energy intensity, and so on. This is something data we are collecting and compiling and already have to a high degree for all these different examples. But this is just today to also show that there are technologies that can connect these dots. And the choice of technology should really be governed by the task at hand, which is very much defined by the quality of the waste stream you can get. And with that, if you have any questions, feel free to approach me, or even better, come at the booth, because you can see all these examples and find experts to talk about them in more detail. Thank you very much.
So, are there 1 or 2 questions, because we have got 2 to 3 minutes left. So now we have got also a microphone. So, Christiane, question is over there. Perfect. I see directly 2 questions, I think.
Thank you very much for the very interesting presentation. But I'm very concerned regarding mechanical recycling. Because in plastics, it is not a monomaterial. It is mixed with all kinds of additives. And I know when you're going to mechanical recycle the stuff, they do all kinds of mechanical tests about the quality. But my big concern is the cocktail of the chemicals that are inside the recycled material. We have the additives, we have the breakdown molecules, etc. So how to handle the chemical quality control of the input of the waste that is every second different, and the output of recycled material.
Absolutely, and this is a dimension that is today maybe still overlooked in many cases, but it comes down to the quality of the waste stream, because if you do mechanical recycling, there's not much you can do, maybe a little bit of stripping, degassing, devolatilization, but in the end, the feedstock needs to be controlled using analytics, using closed collection systems, and so on. Otherwise, you might need a different recycling technology. If this is the case, for example, halogenated legacy flame retardants in polystyrene, of course, you cannot simply mechanically recycle them because you're not allowed to bring products on the market that contain these legacy materials. In this case, you need to go to, for example, solvent-based recycling technology, which is able to remove them. But it comes again, this is one of the criteria how to match a waste stream to a technology.
Okay, perfect. Do we have another question, because we've got 2 minutes left? So.
Yes, it's very insightful. Yeah, so our company called Loop CO2. We use carbon dioxide to new polymer that can be chemical recycled at 100 degrees C with catalyst. So my question is for a new startup like us, how can we, because the scale up is so difficult for a small company, so what would be the best way, maybe working with a different company or like BASF to approaching for this?
I mean, that is a very individual question, because you need to see what need you are addressing. And in this case, what is the timeline and the perspective of CO2-based feedstocks? How does it relate to how much energy do you need, and so on? And probably this is how you need to go into a conversation to see where could that be positioned, and then see what is the timeline, what is the meaningful next step. But it's true, even for a big company, there is this valley of death. It's very hard to scale a technology and take it from lab scale, and Fraunhofer tries to bridge it a bit, right? You showed that. So I think we need to work together, because nobody can work on all of these technologies alone and try to scale everything to world scale.
So, thank you very much one more time. It was very insightful, and I think it's always very good to see what large companies as the BASF is really pushing and doing. So now we are coming to the next topic.